welcome. Apologies, I'm losing my voice, but I'll try to keep this up as much as possible. Welcome to the latest quantum marketplace software for Quantum 2. I'm going to give a brief update, and also get into the lineup and overview and trends, and then a roundtable panel discussion after. So the quantum marketplace raises brand awareness, facilitates collaboration deals and partnerships. QED-C has a web directory publicly facing for each of the companies that's in the membership, and it gives a profile for what each company is doing. So feel free to go there and learn more. Also, this video will be published after on our YouTube channel, and you can go to YouTube/Quantum Marketplace to see that. Today we have Strangeworks, Icosa Computing, infinityQ, Iff and only Iff, and AWS in our lineup. So software for quantum, just a brief update on what's been going on. This is a report from McKinsey. Obviously, quantum technology is a very large market. This is as of last April. And it's really, so the potential economic value, this is the software and the hardware of quantum computing of $0.9 to $2 trillion. You can look at various sources for this, but McKinsey is one of the higher ones. So I think it's good to touch base on, we hear a lot about CPUs and GPUs today with AI. In the future, data centers are also going to include QPUs and NPUs. And we're going to touch a little bit on that, but again, mainly focused on the stack of software for quantum. So quantum computing, just as a refresher in AI, is, quantum computing is all about harnessing entanglement. Both short quantum chemistry work because there's underlying structure in what appears to be random, and entanglement helps us get there. AI can be creative and can be harnessed to better run quantum computing. That is the belief that I have and many others have, and we can discuss that more in a panel discussion today. So in terms of the lineup, wow, voice is bad. Apologies. Anyway, Daniel Lay, who's SVP at Strangeworks, is going to start us off here. Merit from Icosa Computing is a founder. Ariel from infinityQ is the CEO and founder. Samarth Sandeep, the CEO of Iff and only Iff. And then we have Sebastian Hessinger from AWS, who does business development. And with that, Daniel, let's start with you.
Yeah, good morning. Glad to be here. Thanks for the opportunity to share what we're doing. I'll start the presentation sharing. Can you all see it?
Yes, go. Yep. Great.
So at Strangeworks, we're focusing on using quantum and quantum-inspired technologies to solve complex compute business problems today while getting our customers ready for quantum future. It is our perspective that we're sitting in the midst of a computational revolution at the intersection of quantum and quantum-inspired computing, artificial intelligence, and conversational computing. We're making a distinction between AI and conversational computing because from our perspective, AI is providing a lot of the underlying agents and functions and assistance to make these systems easier to program. At the same time, the conversational computing piece is going to make these systems usable by a much broader audience, because rather than programming in unique esoteric functions, we'll be able to interact with these machines conversationally to program them. So we believe that there's a big shift coming, and that the intersection of these three technologies is going to have a huge impact. At Strangeworks, we're providing an all-access pass to quantum computing. You'll see on the left-hand side a list of a large number of our partners, and on the right-hand side, some of the organizations we're participating with in terms of thought leadership. But we believe that between access and thought leadership, we can help move the cause forward in terms of programming and using these systems effectively. So Strangeworks Compute is our primary platform. It's the most extensive collection of compute technologies in the cloud. It includes classical, quantum-inspired, and quantum computing technologies. And we can talk a little bit later about why we believe that that's a proper mix today, just given some of the limitations of QPUs. We have a marketplace of managed applications and access to our partner ecosystem. And at the organizational level, we have a good, solid practice in terms of quantum optimization and QML in terms of help that we can provide to our customers to solve real-world problems. And with that, we're approaching this in a manner that's flexible so that we can work with customers wherever they may be in their quantum journey, from fully knowledgeable people that just want access to the SaaS platform to people that want to work side by side and collaborate on solving a problem. We're working in enterprise business, if you will, and working with some fairly large organizations and demonstrating some really solid results. We're working with a large energy company on unit commitment problems. We're working with a large pharma on drug discovery and de novo drug design, and with another organization on their go-to-market and providing a large ROI on optimizing marketing programs. So the point there is that we are in the mix where we're adding ROI and bringing value today with these technologies to large organizations. The other thing that's happening in our arena is that in addition to the actual platform to access all these quantum and quantum-inspired resources, we've introduced a series of AI aids to work on hands-off interaction with these machines. And what by that we mean a series of assistants and agents to help with research and documentation, the formulation of the problems, the submission and execution of those problems onto multiple platforms, and the analytics for them. So if you look at that left-hand chart in a clockwise environment, that's what we're referring to as Strangeworks workflows. Today, it's really the people that understand scientifically what problem they're trying to solve. We believe that by next year or early the following, we'll be able to do it for subject matter experts, meaning the people that understand the business problem, but not necessarily the compute challenges. And later on, back to the comments made about AI, anybody will be able to use and program these systems. So I've just articulated that. Here's the slide that describes that in more detail. I believe that Mark will be distributing some of these slides later. But it's really at the core of it, redefining the way we can solve problems with quantum and quantum-inspired systems. On the left-hand side, you've got your classical way or traditional way of approaching these systems. And on the right-hand side, the AI-aided approach. And it's just much more streamlined and much easier to use. At the core of it, we are offering a SaaS platform. The top left is the compute resources. The top right is the workflows component. If you're a quantum expert, you don't have to use workflows. You can simply keep working in interacting with these machines directly. The mid layer is those application and marketplace capabilities that I had described, and the bottom is those technologies that we provide access to. That altogether is the Strange. It's accessible through SaaS subscription. But the bottom line is, in today's world, we're looking at a workflow that involves not simply just defining the goals and down selecting these problems, but really verifying that they're friendly or suitable for these systems, and then running iteratively to iterate and benchmark, because today's problems are highly machine dependent, or the machines provide different levels of results for different types of problems. But at the end of it, we are working side by side with a number of organizations to integrate complex compute problems that are solvable with this compute paradigm into their production workflows. Happy to take emails, notes, etc., to talk about how we would go about this. In general, I will state that the core use cases where we're adding the most value, we're seeing the best results, are in the optimization space or in the combinatorial mathematics space. Although we are seeing, for limited size problems, some benefits in chemistry and drug discovery and then engineering simulation analysis. But for the core uses that we're seeing in industry, they have been optimization focused. With that said, I will hand the floor back to Mark. Hopefully
Great.
hit your
Thank you.
target here.
Thanks.
Yeah. Hi, everyone. I'm Mert. I'm from Icosa Computing. We're a startup out of New York City, and we build quantum-inspired intelligence for complex decision-making. So Icosa is an enabler of quantum-inspired solutions. What do I mean by that? First of all, let's talk about applications. We enable quantum-inspired optimization today, which is available today, but we're also building code and software that can run on quantum computers tomorrow. But on top of applications, what we're experts in is model tuning. We tune our models that are inputted into these optimizers to bring practical advantage today. Let me give you some examples. One of them is from NEC. We partnered with NEC to optimize 25,000 stocks at once. And we also tuned this very large portfolio. This portfolio had stocks from not just US, because there's not enough stocks, but from many different countries. And we showed that our tuning can achieve a better performance, for example, in terms of P&L. And this white paper is available. On top of that, we work with Fujitsu, another white paper, where we first showed our reasoning methods with LLMs. But more importantly, we increased the speed 100 times with Fujitsu's digital annealer, another quantum-inspired technology. And more recently, we worked with NASA, USRA, and HPE, NASA's quantum AI team, to write an academic paper on explaining how the reasoning method that we developed, this quantum-inspired or combinatorial reasoning method that we developed works, where we beat, for example, an earlier prompt optimization method from Google. And these are all available at icosacomputing.com/publications. So how does our business work? Currently, we're directly selling our tuning method, as I described, this dynamical parameter selector that we created. We note it as DPS, which brings our customers HPC solutions to real-world practice. On top of that, we have two applications where on top of a fixed fee, we also charge a performance cut. For trading, we already deployed this with customer success. We made our customers more money, and we got a cut out of that. Instead of using their methods, they used our trading technology, and they achieved better performance. Reasoning, this more recent application works directly with unstructured data. So you don't have to have structured data. We built this on top of large language models where we can get text data, for example, and get solutions out of that. And with this, we actually expanded into insurance and healthcare. We just onboarded design partners here, and we're tapping into a very large regulated industry market. So that's finance plus insurance plus healthcare, where we identified inefficiencies in decisioning. So currently, quantum industry works a lot in academia and mostly with POCs. There's a lot of amazing and interesting science going on, but it's very hard to get to practice. So on top of scaling combinations natively with the applications I just described, with physics-inspired Ising solvers, that bring us this 30x scaling advantage. So 30x more discrete variables. And this number is actually growing, as maybe you'll hear from other speakers today. But we also bring practical value to customers today with our dynamical parameter selector. And this, yes, in fact, increases performance, such as P&L or Sharpe ratio for finance customers, but also explainability of AI systems. So it actually increases the trust that a customer feels towards an AI agent, because you're seeing what's going on behind. With combinatorial reasoning, you can actually visually see the reasoning process behind the decisioning process of an AI agent. And feel free to check out our software at api.icosacomputing.com. We're raising our second round soon to build excellent enterprise SaaS but also to host our own GPUs instead of relying on others with multiple open source large language models. We completed 2 accelerators before. One was Duality, amazing accelerator, hosted by University of Chicago, actually how we got introduced to QED-C. We also completed Creative Destruction Lab in University of Toronto, another amazing program. We also worked directly with quantum-inspired and quantum computing providers. So if you're interested in bringing your solutions to practice, achieving more performance out of your amazing solutions, please reach out to us. And lastly, if you're interested on this visualization I just described on reasoning, please check out our demo, demo.icosacomputing.com, where you can see the decisioning process visually. Thank you.
Thanks, Mir. Ariel.
So hello everyone, my name is Aurélie Louis. I'm the CEO and founder of infinityQ, and today I'm excited to introduce you to TitanQ, our cutting-edge platform designed to tackle some of the most complex optimization challenges industries currently face. At infinityQ, we believe in creating simple solutions to impossible problems. And TitanQ, a real time machine, simplifies these complex problems and challenges and delivers faster, more accurate results, allowing you to focus on what truly matters. What sets TitanQ apart is our use of quantum-inspired technologies. Unlike traditional solvers that really rely solely on classical computation, TitanQ leverages the principle of quantum mechanics to enhance processing power and optimize solutions in the fraction of the time. Our approach uses quantum-inspired algorithms to model and solve complex combinatorial problems like routing, scheduling, resource planning, error tracking, portfolio optimization, you name it, and with unprecedented speed and precision. This allows us to unlock new levels of efficiency that were previously out of reach with classical methods alone. So TitanQ is infinityQ's flagship platform designed to handle the most difficult optimization problems. And as I said, it's not just a solver, it's a time machine, a strategic decision-making tool that integrates seamlessly with your current workflows. We have customers that are really happy with it, such as Siemens Energy Ventures. And one of the problem we solve, it's a real-world example, the grid optimization in the energy sector. So as you know, managing energy grids involves balancing supply and demand across large networks, and efficiencies can result in huge losses. With TitanQ, you can quickly optimize the distribution of energy to minimize cost and ensure more reliable service and better than your competition. Now let me show you TitanQ in action. So I wanted to show you the dashboard we have, and I have a couple of demo, and one example is the last mile delivery. It's the routing problem we solve for 10,500 packages. So we put the file, we can modify some constraints here. And then when we compute, the platform start putting the different packaging into clusters. So if you have different drivers, it optimizes the distribution of the packages. And then we create the routes. So the example I took is the island of Montreal. And you would see this is the warehouse, and the idea of the solver is to give the different clusters, as you can see, and we can have the different routes. Oops. Looks complex because we have a lot of different routes, but we can see direction. We can see the routes. For example, if we take the blue one, it shows the different stops.
And you said this is 10,000 packages?
10,500 exactly.
Wow.
In just less around 30 seconds. So one of the value proposition is being really efficient, accurate, low energy, and one of the main advantage, especially compared to AI, is the explainability of the model. So we can really understand what's in the model. So there is no surprise, and the customer can really apply all the knowledge they know and understand what's going on. It's not a black box. So TitanQ is more than just a platform. It's a tool for transforming your operation, and it can be across a lot of industries. It provides the speed, the precision, the solution that are faster and more accurate than traditional methods. And as I mentioned, the explainability, which is a big advantage, especially compared to the AI models. And the scalability, we can tackle a large range of problems, and we are very good at very large problems. And we are actively looking for partners who are ready to take their operation to the next level, leveraging TitanQ to optimize and innovate across their industries. If you're interested in collaborating with us and becoming part of this future of the quantum-inspired technologies, we'd love to explore how TitanQ can help drive your success. Thank you for your time, and I look forward to discussing potential partnerships.
Great, thanks. Samarth.
Hello, everyone. Good morning. My name is Samarth Sandeep, and I'm the CEO of Iff Technologies. So we are a bioinformatics company, but we use quantum information science, quantum chemistry, and quantum devices towards solving some of the hardest problems in bioinformatics. Specifically, we're very interested in solving the problem wherein we have, say, a drug that interacts with a protein receptor, but we want to see how that protein receptor is then interacting with immune proteins, or how that drug is then being cleared when it's being processed by a patient. So this is a problem that not many companies in our field focus on. Many are focused more on lead generation. And now there are a ton of software tools, everything from in silico medicine to many others that can provide these solutions. But we really are seeing that for many larger pharmaceutical companies, especially, that they get stuck in many of the trials if they're not able to really understand these protein-protein interactions. So we wanted to build software to solve this problem. So we have done just that. So currently, we actually have a pipeline going all the way from literature analysis all the way through to protein binding. And our work actually began back in 2020 when we worked with a food science professor at UC Davis named Nitin to come up with a way to take large protein structures, break them down into smaller subunits that had more of the important atoms that could be used within existing docking software such as Autodoc, Bina, and ZDoc, but still provide meaningful results. It's from here that we've been able to then develop this suite of quantum technologies and are continued to be interested in developing technologies towards solving the hardest problems in bioinformatics. So specifically, we're very interested, as I was saying, in quantum chemistry, quantum information science, and quantum devices, in that we really see this sort of nexus being created, wherein we have these quantum chemistry methods that have existed now for decades for looking at subatomic interactions. But we now have quantum information science, really quantum algorithms that have taken some of these sort of NP hard problems and turn them into problems that are BQP hard or even QMA hard, and can therefore be approximated with quantum algorithms or quantum approaches. And now we even have quantum devices where we can take these quantum algorithmic approaches and get to try them out without having to do this really rigorous classical code setup. So this is the sort of future that we are working within, and we hope to use this sort of methodology to solve some really hard problems, such as multi-sequence alignment. And we, especially in the cases where AlphaFold and other machine learning methods like ESMFold seem to fail, where there is not a lot of data on said protein, and we need to do molecular dynamics or some other type of atomic modeling before we can even begin to do structural homology or sequential homology. So towards this end, we're very interested in collaborating with a number of you. We're very excited to be members of QED-C and have been so since 2021 when we joined the QFarm group. So we're very interested in continuing collaborations with pharmaceutical companies who are looking into quantum technologies and are especially interested in solving the problems related to COVID-19, especially as the long COVID patient demographic continues to grow day by day. We're very excited to continue working with quantum vendors. Actually, here I'm very excited to be in the same panel session with Sebastian, who was one of our first partners when we were working with IBM back in 2021. But we have worked with a number of quantum vendors on looking at some of these quantum chemistry, quantum information science problems. And we're interested, especially in companies that are looking at pulse level controls and ways they can standardize those kinds of approaches. And you've probably seen myself or my co-founder Kirk at various QED-C TAC meetings advocating for this level of interaction. So if any of these things are of interest to you to work with us, please get in touch. Our website is not the most up to date, so if you want to hear from us, please definitely follow us on LinkedIn. I'll put the QR code to our LinkedIn page here. Thank you so much.
Great. Thanks, Marth. Sebastian.
Sebastian Hassinger. Thanks for having me today. I'm very happy to be here. I'm with Amazon Web Services. And as Sam Marth pointed out, I've been working in the quantum industry for quite some time. I was with IBM until September 2021, and then joined AWS. AWS, of course, the provider of IT infrastructure in the cloud. And so I wanted to tell you about our Bracket cloud service, which is our quantum infrastructure. It's been in GA for about 5 years now. It's just over 5 years. We provide access to quantum devices in an integrated way. So this is really the only fully integrated multi-platform cloud service. And by that I mean it's a single stack, a single technology stack means for accessing quantum devices in the cloud in a fully integrated way. So it's integrated with the rest of the AWS cloud services. And in addition, the devices themselves, the technology is integrated, the pricing is integrated. The whole service is geared towards making it easier and more uniform to access and manage your access to these devices, which we really feel is incredibly important in this phase of quantum computing that's highly experimental. There's still a ton of unknown factors in terms of how the technology will develop, which modality of qubits will turn out to be useful for which types of use cases, which algorithms will be useful. All of that uncertainty is what's challenging the ISVs, the quantum hardware providers, the other users of these technologies today. And the role of Bracket in many ways is to try to simplify the parts of the problem that are simplifiable at this point. So Bracket itself is a full sort of life cycle service for building quantum experiments at this stage. The end users of Bracket are everybody from enterprise end users to academic researchers, as well as ISVs who use Bracket to access multiple devices within their own offerings, and quantum hardware providers that use Bracket as a a route to market and a means for accessing the customer segments they're going after. Bracket itself, you can use it to monitor the state of devices, to track the status of your own tasks, to build algorithms, and to run on both simulators, managed simulators in the cloud, and actual devices at hosted third-party sites as well. The means for accessing, there's the console itself in AWS, which should be quite familiar to anybody who's used AWS, but then also there's an open source Python SDK, which can be used to access the API. More recently, in the last year, we launched a new feature, which is a subset of Bracket called Bracket Direct. I just wanted to highlight that. It's still in development. It's really interesting, I think, because it's opening the door to different modalities, even within the experimental devices that exist today. So this is a way for end users to engage the quantum hardware provider and also ISVs and other partners directly. There's a sort of almost small marketplace within the Bracket console of direct offerings. And these can be experimental devices. For example, IonQ's Forte device is not on the public system, the on-demand systems, but it is available by reservation, or it can be experimental features on existing devices. So, for example, the QERA Aquila device in Direct has experimental features like alternative geometries to the square lattice that they normally offer, and also local detuning. And we expect other beta features, experimental features, and experimental devices will be surfaced in the Direct offering as well. And also, as I said, ISVs and consulting offerings can be made available through the AWS marketplace and then surfaced in Direct, where they can be engaged by customers directly. Getting started, the Quantum Technologies blog has examples of all of these types of use cases, examples where we collaborated with academic researchers, collaborated with industry, JPMC and BMW, Airbus, et cetera, as well as ISVs, Strangeworks, IFF, Icosa, and actually, I don't know if we have collaborated with infinityQ yet, but we certainly are open to it, and also consulting partners and public sector institutions as well. And then we also have self-paced training. So the Skill Builder site on AWS has sort of a level 100 and level 200 class. They're all self-paced, and then a digital badge for knowledge assessment that can be used to build skills and get started. So thank you very much. A moment of shameless self-promotion. I'm also working on a book on the history of the field of quantum computing with O'Reilly. The first 12 chapters are available for free on the O'Reilly learning platform right now. The full book is due out. I'm still working on the last chapters, but it'll be out in 2025. So thank you very much for your time.
Great, thanks, Sebastian. Let's get into the panel discussion. Okay, so this is a conversation that's going around a lot right now. So with recent trends emphasizing the need for fault-tolerant quantum computing, example, utility scale instead of noisy intermediate scale quantum. How is your organization approaching this? I'm just going to go right back to you, Sebastian, and kick this off.
Sure. I mean, thank you, Mark. So it is an interesting moment in time. I think, the last 12 months, there's been really outstanding results and also plans discussed around logical qubits of various types using LDPC or surface code or additive codes from the various hardware vendors. I think also there's interesting approaches to error mitigation. When you talk about utility scale, there have been really interesting scientific experiments by Martin Savage, for example, doing over 100 qubits and something like 13 or 14,000 gates using error mitigation techniques to get usable signals. So with the Bracket service, what we've done is, I mentioned sort of part of it is trying to future-proof, right? There's so much uncertainty in the way the technology is developing, the way we access the technology. Bracket itself is kind of an open architecture. So things like the MITIC framework from Unitary Fund, which is an error mitigation framework where you can plug in different approaches to error mitigation, that's fully integrated with Bracket. Penny Lane from Xanadu is fully integrated with Bracket. Qiskit we've built a bracket provider for Qiskit code. So basically, as the approaches evolve, as the hardware evolves, we'll be continuing to upgrade or update the hardware available from vendors, and also integrate new tooling, new frameworks on the software side to help customers sort of adapt and evolve as the field evolves.
Great, thank you. Hey, Daniel, why don't you go next on that?
Sure. It's not dissimilar to what Sebastian just mentioned. It's really about being able to support the whatever new techniques and methodologies people are putting forth, and make sure that we keep abreast of it. As a neutral provider of access, we have to keep up with these trends and make sure that we support them. So with that, I don't think there's anything that is specific to one provider or one modality, but essentially we have to keep up with these things.
Yeah, great. Merit.
Yeah, so our answer would, maybe it's a bit controversial, but we would just use whatever that works. So if there was a fault tolerant quantum computer tomorrow that was optimizing over, I don't know, 1,000 to 10,000 stocks. In fact, we heard from infinityQ today. I think they can go up to 100,000, right? So we just use whatever works, and our approach is using maybe potentially our optimizers to get the pulled applications towards fault-tolerant quantum computing or quantum computers by creating more efficient algorithms, more optimized circuits, for example, for circuits-based quantum computers.
Great. Ariel.
So in our case, our main focus is the development of our quantum-inspired algorithms that are done in-house. We don't say that quantum won't come, so we keep an eye on the evolution of quantum. We have, I would say, a research stream. We have strong academic relationship. So we are following the progress of quantum. So when everything would be ready, we would be able to integrate them with our technology. But our current focus is really on commercializing, going to market with what exists and what brings value today.
Yeah, great. Thank you. Samarth.
Yeah, so we are doing what we sort of have always been doing, which is really looking at the full stack of whatever quantum device we're using. So as we know, quantum devices are not just the chip, right? There's the FPGA that actually sends instructions. There's the cooling. There's a lot of other components. So we try to get an idea of exactly like what's happening and how it's happening. And then from that, how we can do some kind of pulse control or whatnot to enable some kind of really effective modeling of our system. So in the past, I will say what's really changed is we don't sound as crazy as we used to. I would say like a few years ago, like when we were saying we wanted to do Lindbladian work for some of the quantum chemistry we were doing with UCLA's quantum biology team, and we were looking at pulse level control. It was a relatively newer area, I guess, for like the hardware companies, and they were not as interested in that kind of work or offering that kind of access. And then they tried all the error mitigation stuff, and it didn't really pan out as they thought it would. And now we're finally seeing people like actually being interested in working on this stuff and wanting to give us that level of access. So it's really becoming a lot simpler to work with partners on solving some of these problems. So that's sort of our approach.
Got it. Thank you. So, Daniel, I think you suggested this one. So who's consuming your products today? Experimentalists, scientists, the quantum curious. Daniel, I'm going to start with you on this.
Yeah, I think it runs the gamut, right? On our end, we see, let's say, 3 different types of user categories on the Strangeworks platform. The first one is people that are quantum knowledgeable and simply want to use our system for accessing the quantum hardware, and those are not as many today, but they're a solid community of highly knowledgeable people. The next stage is people that are, let's say, mathematically inclined that know how to define their problems using objective functions and can describe the problems in equations, if you will. And what they need help with is simply mapping them to specific types of hardware devices. And our scientists are happy to provide that level of scientific support to do that. And lastly, you have the organizations that are very, very early to have not started their quantum journey and want a guided engagement with professional services, if you will. So those are the three categories, and the latter category seems to be larger corporations with large research or innovation teams that are looking to get further involved in using the technology.
Yeah, I'm curious. How does this break down for Strangeworks, if you're able to share, in terms of like how much percentage of each three?
So if you look at it from a revenue perspective, the guided journey is probably the dominant factor. If you look at it from a number of users perspective, I would say that middle of the bell curve is where we're hitting, which is people that are mathematically inclined but not necessarily device knowledgeable. The quantum knowledgeable crowd continues to be a very, very small community for us.
Yeah, great, thank you. Merit.
Yeah, I think that's a great distinction that Daniel made. I agree. For our organization, it's pretty similar. We quantum aware customers, and they usually have a problem related to a specific industry, such as bringing their HPC solution or quantum inspired or quantum based solution to practice. Again, we directly sell our model tuning, but also we look at applications, and in applications we can have customers that are zero quantum aware. They only have a very specific problem, such as increasing P&L. So customers from hedge funds, banks, mutual funds, they want a specific outcome, and they don't really care about what we do underneath. Sometimes like it's a fancy word for them. They maybe internally discuss that they're using a quantum inspired solution, but it's not a key driver to our sales. The key driver to our sales is a practical outcome, such as increased Sharpe ratio or better profits with discrete variables, discrete constraints. And that is, I guess, not even the curious part, but the part, the risk taker, another category I might define.
Okay, great. Thank you. Ariel.
Yeah, I agree with Mert that the customer we have are really people who try other solvers and are not happy with the current results. So either their problems are too big, it takes too much time, and they are always looking for better solvers. So providing this type of solution, like the optimizer on steroids, that's what they are looking for. And sometimes using quantum, they can be scared. So it really depends on the customers. So the focus is really on the benefit and what can be done, the value we can bring instead of the tech itself.
Yeah, thank you. Samarth?
Yeah, so I would say we've evolved a little bit. So when we first started, we were definitely focused on, okay, we're going to have this sort of API or this tool set that's going to be just aimed at bioinformatics researchers, and that's going to be the most useful. But I think what we've been working towards is sort of a varied approach. So theoretically, somebody can take a look at our pipeline and use all the tools from start to finish if they want to do that. But realistically, we've had, so I think on my slide, I had shown Mount Sinai, for example. So like we're working with an oncologist there. So he is somebody who would be using more of the literature analysis tool and binding within that. So he wouldn't necessarily be doing a lot of the bioinformatics work because that's not his background. But then there are other folks that we've worked with in bioinformatics that are within like drug discovery, like labs or whatnot, that would be more interested in some of those other protein binding tools. And we've also been more recently working with other researchers who are trying to develop new approaches towards how they can even set up their software stack for developing some of these protein binding and protein folding approaches. So yeah, I would say our user base is pretty varied within the bioinformatics community, as it were.
Okay, great. Thank you, Sebastian.
Yeah, similar story in many ways. There's, Quantum Curious is probably more on the enterprise side. It's sort of exploring where the technology may have impact in the future for them. There's a smaller number of enterprises that are deeply invested. I named some of them before: BMW, Airbus, JPMC, et cetera. But the majority of users on the service are quantum researchers. They're either trying to drive the field of quantum forward with things like error mitigation and error correction or algorithm design, or they're scientific users who are starting to use the devices to do novel science. I mean, I think the devices that are hitting a level of maturity where they're starting to fulfill Richard Feynman's kind of vision of if you want to simulate a system from nature, you need a quantum device. So the utility scale sort of messaging from IBM, for example, or the quantum spin fluid simulation that Lucan did on the neutral atom device at Harvard, or some of the research that's been done by Google. Those are all sort of novel scientific results. The other sort of emerging trend, I think, is national level public sector investment in quantum initiatives. Things like National Quantum Initiative in the US, or Quantum Delta, or in the Netherlands, National Quantum Computing Center in the UK. And that's primarily bringing together the research community, but as a way of more effectively deploying resources, and also more effectively harnessing that existing knowledge to try to foster the development of a broader ecosystem within that country. And that the one sort of new complication there is that often involves either developing devices on site or buying and deploying devices on site as well. So there we're starting to see challenges from our customers of how do we manage the access and the operation of these on-premise devices in conjunction with cloud devices. Because if you buy and deploy, or build and deploy, a single modality or even a couple of modalities, that's still not going to fulfill all the needs of your researchers. So you're going to want to have access to other devices from other vendors to sort of round out all the resources that you make available.
Yeah, great. Thank you. So going right back to you, Sebastian. So what question are you hearing most from your customers?
From industry, it's what's the use case, right? And I think it's really refreshing, honestly, to hear the ISVs, the people on this call who are bringing solutions to the market. At the end of the day, the commercial user doesn't really care a whole lot about what the chip is that is underpinning the solution, right? It's more about commercial value and solving a problem. And I think that's really a healthy approach for an ISV, for a consultancy, to try to figure out what customer solutions exist, irregardless of how they're actually powered into the covers. So there's that whole aspect of it, and that's kind of part of the broader landscape from an industry perspective. Like, compute IT is getting more and more complex with GPUs and FPGAs and more exotic sort of flavors of computing, and that's I think something that the Strangeworks solution, or these more targeted solutions from the vendors on this call are all highlighting. On the sort of longer term strategy of like, where is quantum going? There, it's really just a matter of what are the modalities, what are the skills I need to invest in to make sure that I'm taking advantage of these quantum specific capabilities first and most powerfully, right? And I think the emerging topic that we'll see in the next 12 to 24 months is going to be logical qubit programming, circuits around logical qubits instead of physical qubits. And there, you mentioned AI in conjunction with quantum. I do think that the added complexity of managing and programming with logical gates and logical qubit operations is potentially somewhere where AI tools may help a lot, because the complexity is just going to explode, right? With the numbers of qubits you're actually trying to manage, and then the extremely complex operations you have to do, like magic state distillation for T-gate operations on logical qubits. That's really, really beyond the scope of what you want to be dealing with if you're just trying to solve a particular problem or simulate a quantum system. So that's what we're seeing.
Great. Thank you. Samarth.
Yeah, I would say for our clients today, the biggest questions that they're asking are, how does the SARS-CoV-2 spike really work? Does it really interact with these type of molecular models in this way? And how can we better understand this? I would say that, that most of our sort of client or customer focused discussions are really on the bioinformatics specific work that we're doing, and not as much on the quantum. We have had questions in the past where people, I think one of the funnier questions we had was somebody had read The Economist and said, well, in here it shows that they achieve a quantum advantage in this way. So how does that relate to what you're doing? And so we had to sort of describe like what exactly was the use case or whatnot. But yeah, I would say that that's the biggest question currently that we're getting asked is, how do immune proteins really fit into the SARS-CoV-2 ACE2 binding story for developing COVID therapeutics, and how does that change with long COVID or whatnot?
Yeah, got it. Thank you, Ariel.
In our case, it's more what type of speed up of better performance can your quantum-inspired approach bring? For example, recently we had one of the largest US banks that sent us a couple of problems, and we ran it on the machine and sent up results with 1,000 times faster than their current solvers. So it's the way we attract customers, and we also respond to their question of what speed up, what better performance can you provide with your technology.
Great, thank you. Merit.
Yeah, I mean, very similar to Oriol's answer. Usually customers ask, what can you improve for us and by how much? So that we need to be very clear on that. And after the acquisition process, once we start working with customers, they care quite a bit about how things work. For example, I described at very high level, we have a machine learning based tuner called Dynamical Parameter Selector, DPS. And usually we get questions like, okay, how does this work? Why does it work? And does anyone know who loves explainability more than scientists? Does anyone want to take a guess?
All right, go ahead.
Traders.
Yeah.
Hedge fund managers.
Yeah.
They hate boxes. So we need to be very clear on what's going on underneath. And especially when you're making a high stakes decision, you don't want a black box. When you're diagnosing a patient, when you're making an insurance matching or making a trade, you want an explainable result. So we get a lot of questions on this, on what's going on underneath.
Yeah, got it. Daniel.
Yeah, I'm hearing we're hearing a common theme here. So we're all hearing very similar questions or concerns. The other one that still keeps coming up, right, is when will quantum start, adding, you don't want to use the word advantage, right? But at what point do we start getting, enough value at scale that especially large enterprises says, when should we be, fully jumping in, right? There's still that dichotomy of a tremendous fear of missing out in terms of not wanting another ChatGPT moment, if you will. But at the same time, many still sitting on the sidelines waiting for a full error correction or such a type of milestone, right? So there's still a lot of questions being asked about when is the right time to adopt the technology is what we're hearing a lot of.
Yeah, great. Thank you. So, in terms of how do customers potentially best assess various quantum computing software solutions today? So, and how important, in terms of the progression here, we talked about this a little bit, but how important is, hardware system and application benchmarks in this assessment? Let's start with Sebastian again.
Oh, sorry, I was answering another question.
Yeah, no problem. No problem.
I mean, this is the central question, right? I mean, every device, even from run to run, devices vary, right? I mean, they're incredibly idiosyncratic. So there's really no other question that's as important. And it's really from every angle as well. It's trying to figure out how to get. One of the reasons we launched Direct was that we realized that customers trying to get the sort of best experimental results out of any particular device for their data for their experiment, they really needed to have the hardware vendor, providing hands on the device in many ways, right? If you look at sort of nature paper level results from it, that's been run on real hardware, it's almost always been from a hardware vendor that owns their own device, right? There's sort of an army of PhDs that are swarming the superconducting qubits from IBM or Google or whatever when they write these nature level papers. So that's the reality today. Obviously, everybody's hoping that will continue to improve fidelities, will improve stability of the overall systems. I think that I mentioned the sort of on-premise development and deployment. I think that's another sort of lever that's driving vendors to think through these reliability measures, right? So LRZ, for example, Leibniz Supercomputing Center in Germany, they've developed an open quantum device management interface, QDMI, I believe it's called. And that's a set of measurements and criteria for trying to evaluate the stability and the performance of a given device in a generic way. Those kinds of standards are helping the whole field evolve towards more and more sophisticated and more reliable devices. But it's also it's everything from system integration, system operation, all the way to better understanding of the quantum physics that underlies the phenomena you're using for computation. So talk about full stack, right?
Exactly. Daniel.
Yes. On our end, yeah, it really is a buyer's challenge, right? Because the results are so problem dependent and so machine dependent that it is challenging for them, right? So what we're finding in our practice is that you actually do have to formulate the problems in a manner that's as portable as possible, and then try multiple solvers or multiple backends to get the best results.
Yeah, great. Samarth.
Yeah, so definitely. So I'll first talk about like very briefly how people are doing this currently. Definitely,
Yeah.
I think a lot of people are reading reports like from groups like McKinsey or other groups to see like, okay, what exactly is quantum and trying to get an idea for that. But definitely some of these reports are not the greatest in that they include other potential machine learning methods or other methods, and they sort of describe how there could be a quantum speed up without really talking about what specifically they're doing that is quantum oriented. So in terms of successful customers in finding quantum computing software, they're usually people who are actually thinking about quantum chemistry problems, or they're thinking about topology problems, and they're looking at solutions like PySEF or whatnot already. And they're like, oh, how can we use a quantum device to better improve this solution? And that is where hardware system and application benchmarks are extremely important. It's been really great to see QED-C sort of play a really big role in this, especially we saw that recent paper that came out this year on QAOA benchmarking, which has been extremely helpful in seeing how different Trotter steps, for example, can affect performance of the problem. So seeing those kind of benchmarks on a more fundamental basis for exacting gate operations will be really good for different devices, so that someone can say, take a quantum chemistry model and know that, okay, it will work with this type of success rate on this device versus another device, for example.
Yeah. Thank you. Ariel.
In our case, I think benchmarks are very important. So, customers can really understand what value can be brought with these different types of computation, and how opponent hardware is. We also noted that a lot of customers want on-prem solutions, a little bit what Sébastien were mentioning before. So it's, for confidentiality and IT reasons. So it's something we need to take into account when we provide the solutions.
Oh, great. Thank you. Merit.
Yeah, I mean, benchmarking is quite important. So I think quantum computing is covered. So I'm going to take this question a bit differently. I'm going to talk about quantum-inspired optimization specifically, or Ising machines. So if you're solving a very, very large problem, let's say more than 30,000 variables, fully connected QUBO, or some sort of combinatorial optimization problem, it's pretty difficult to know the actual solution to that problem is. So you think you find the ground state, speaking of chemistry, you think that you find the ground state of the Hamiltonian, but more often than not, you're just finding some random energy. Even if you're still getting the same energy multiple times, maybe you're in a local trap. It's not the actual global optima that you're trying to find. It's a trap, and it might be very far away from what you're trying to achieve. And unfortunately, we see this with a lot of papers. What's happening is these papers claim that they're finding the ground state of these Ising Hamiltonians, or they're providing an improvement to existing solvers. And usually, if you look at Ising machine literature or quantum-inspired optimization literature, you'll see that the comparison is usually to simulated annealing. And does anyone know when simulated annealing came about? The year when it was
I don't know.
1983. So
oh wow,
40 years passed, and we're still comparing our optimizers in such a edge science like quantum computing or Ising machines optimization. We're still using simulated annealing as a benchmark. So this is a fundamental problem with the scientific research, and unfortunately, it's not like no one's at fault, because there's no way to find ground state. Well, there is a way. You can use planted solutions, which means you know the solution a priori, you know the solution beforehand, and you create a problem out of your solution. So you have your solution in your pocket when you go to the optimizer, and then you know how well your optimizer behaves. But not a lot of papers look at planted solutions. So this is, I think this is very important for just in terms of scientific discourse. In terms of customers, for example, our customers, as I mentioned in the previous question, they care about a real-world metric that we're trying to improve. They don't really care about what the ground state is. One example I can give is about our combinatorial reasoning use case, where we looked at large language model performance without using our method, combinatorial reasoning, just asking I think around 10,000 questions to the large language model, different questions, reasoning style questions. This data set we used in our paper was Big Bench Hard. It's a data set built to benchmark large language models. And we showed an improvement over zero shot meaning just asking the LLM directly without using CR. And we showed the performance improvement, and you can see per sub data set. So category, like movie recommendation, for example, we were really good at movie recommendation style questions. So those are much more understandable, and those kind of communicate very clearly to the customer. So when you're in a very hard to understand field like quantum computing, translating that to real world metrics is very high stakes for us at Icosa.
Yeah. So you said the acronym CR. What did you mean by that?
Combinatorial reasoning, CR.
Yeah. Sorry. Okay. Thank you. Yeah. Okay. Great. We sort of answered that one already. So some of you sort of already do this already. So I'm going to go right back to you, Mert. So what is the future of simulation in quantum computing?
Simulation, do you mean by like classical simulation?
Quantum inspired, et cetera, et cetera. As hardware improves, what's the future?
So, I mean, GPUs are progressing exponentially, and so it's of course complementary technologies. Like one of your first slides was GPUs, CPUs, QPUs, NPUs. In many cases, we're seeing that like GPU-based quantum-inspired algorithms are doing quite well. Yeah. And yeah, exactly.
They are doing quite well right now, right?
Yeah, so, exactly. So, simulating quantum circuit-based quantum computers is still a very interesting area of research. Of course, not everyone has access to quantum computers. In fact, it's quite difficult to get access to quantum computers. Well, thanks to Bracket, everyone has access, but funding is an important issue. If you're like doing a PhD, you gotta jump through many hoops to get access to a quantum machine. So usually people have to deal with simulators. So it's very, very important for the science of quantum computing that we have proper simulators and they're properly utilized. They can be accessed, and GPUs are. I don't think I'm in the wrong in saying that GPUs are more accessible than QPUs currently.
Today.
In simulation, yeah. In terms of simulation, as Feynman suggested in the 1980s, right? Quantum computers are built to simulate nature because nature is quantum mechanical. I still think, maybe I'm overly optimistic or idealistic, but I still think that quantum computers' first use case will be simulating nature. Maybe Samart can talk more about this, but simulating quantum mechanical processes like chemical situations, those are going to be the first solid use cases in my opinion, but I might be wrong, so take it with a grain of salt.
Great, thank you for that. Samarth, let's just go. He keyed it off right to you, so let's go back to you.
Yeah, definitely. Simulation of quantum chemistry models on devices is going to be a no-brainer. I think that's definitely something that is going to happen relatively soon. I think an interesting panel discussion I heard recently, well, I mean, recently as in June, but there was an economist session with Dorit from Kedma and Scott Buchholz from Deloitte and a few others, where they're talking about the future of quantum. And I think everyone there, except for Dorit, was saying like quantum plus machine learning is going to be the future. But Dorit was like, no, quantum simulation is going to happen. And instead of 5 years, we're actually working towards this timeline where it's going to happen within like 1 to 3 years because of what our partners at Quera and what our partners at other quantum hardware companies are actually able to put out. So it looks like that is definitely what's going to happen. I think the hard question really comes down to what types of chemistry problems. So I think a really good recent paper that talks about this is a paper called Quantum Computing for Corrosion-Resistant Materials and Anti-Corrosive Coatings Design from Michael Bremner, and team from University of Technology Sydney, where they talk about how the NP hard problem of fermion modeling can be made QMA hard, and some of those QMA hard aspects can then be made BQP hard or even simpler, depending on what type of dimensionality you have in your problem. So I think that really clearly broke down, okay, like the near-term problems are going to be sort of these simpler chemistry problems that we're going to model. And then eventually we're going to get into these much more interesting chemistry problems. For us, we are very interested in the ability to do multi-sequence alignment from molecular dynamics. Like I was saying, we have AlphaFold, we have ESMFold, we have all these methods that can do this sequence homology using transformers. But these homologies are not very good for proteins that are not very well known. And that's where you need the dynamics and the actual chemistry models. And that's where we're hoping to go, is that MD goes to then figuring out what those improved sequence homologies are.
Okay, great. Thank you. Ariel.
So I agree with Mert and what have been said, that the quantum simulation will really bring a lot to simulate nature. In the case of optimization, I still believe that the quantum-inspired technologies will have a long life, even if quantum computers arrive tomorrow. Because it's demonstrated that so far optimization can be solved with the simulation very well, and for some companies that's all they need right now. So and even in the future.
Yeah. Thank you, Daniel.
Sorry, I was speaking to my mute button. I agree with everything that's just been stated. The short term is, in my opinion, very well aligned to physical simulations, right? Whether it's molecular structural type of things or chemistry. Longer term, we shall see what else comes with it. And the question really becomes, where can you leverage this finding the lowest point of energy to solve complex problems, right?
Yeah. Great. And then Sebastian, final word on this.
Yeah, two things just to point out, like things like QERA, for example, are not universal computing platforms yet. They're analog. It's an analog Hamiltonian simulation device, and there's other possible limited use simulators that will far exceed what we can do with a universal quantum computing in the near term. So I think that's really interesting for physical simulations. And then the other thing, just to point out again, back to the logical qubits and error correction, there's sort of a magic number. We get to roughly 50 logical qubits, and it's just not simulatable anymore. So in terms of GPUs and other classical approaches, quantum, once you get to something that you can model on 50 logical qubits, you're just not going to be able to approach that classically. So that's when we're fully in the quantum realm.
So you're claiming 50 logical qubits.
50 logical of sufficient fidelity, that's beyond the ability to, and again, fully entangled, right? You get sparse entangled simulations of large numbers of qubits. So if you see somebody saying I'm simulating 200, 300 qubits, ask them how many of those are entangled with one another. But if you get 50 fully entangled qubits, operating at high enough, like long running computations, that's not classically simulatable.
And with sufficient gate speed.
Yeah, well, that's the whole wall clock question, which is like, if it can do a perfect simulation, but it takes years and years and years to do it, is that actually useful?
Yeah. All right. Thank you.